All right, this is section 1.7 on transformations of functions. We're looking at today basically all the different things you can do to move parent graphs around, all the different types of transformations we can make. So our essential questions today, the first one is to use vertical and horizontal shifts to make sketches of graphs, so understanding what that might mean. To use reflections to sketch graphs, so how does that work and where can you reflect? And then using non-rigid, which means things that change the shape a little bit, transformations to sketch. So kind of those are our big three to be able to talk about. So let's kind of define those three first of all so we know what we're talking about. A vertical shift is an example of a rigid transformation. You're shifting the graph up or down. So it's a shift in the vertical direction, so either up or down. We call that a rigid transformation. If something is rigid, that means the size and shape stays the same. So rigid means it doesn't move. The shape, I guess, so the actual shape of it stays the same size. So the figure is congruent, but it's either shifting up or down. Horizontal, it's the same kind of idea. We're shifting either left or right though. So it's a left or right shift, and that is also a rigid transformation. The entire picture moves left or right, but it stays the same size and shape. The non-rigid transformations cause some sort of distortion. It's a change in the shape of that graph. So it's a change in the shape of that original graph. So that's like the stretching and shrinking, things like that, that maybe you remember doing before. So it's a change in the shape of that original graph. So something's happened to it to distort it. Kind of like when you get, if you get your eyes dilated, some people call those dilations as well, non-rigid. So it's changing the size and shape of that graph. All right, so let's talk about how we can do these shifts. So I think a lot of this should be familiar, and we're going to be using either your graphing calculator or Desmos to kind of explore this a little bit. If you were here kind of live in class, we'd be doing a lot of that, but this is just kind of giving you the nuts and bolts. So in order to shift our graph either up or down, so we're going to do this from a function notation. So an f of x, if you want to take a function and shift it up, basically what you have to do is you have to take your original function and add something to it right at the end of that. So they're going to use, I'll just use a different variable here. If I want to define a different function that's been moved c units up, I would take whatever my function is, f of x, and I would add c to it. So we're going to do lots of examples to illustrate this. If you want to move c units down, exactly the same thing, but we take that function and we subtract something from it. What if you want to go left and right? Well, left and right is the horizontal. That means it needs to be in with the horizontal variable, which is the x. So if you want to shift to the right, you want to take and see how far c units to the right is going to put you. That means in with the x, we're shifting x minus c. Now, it always bothers people. Why is it minus? It's distance from 0. So how far are you moving from that original location, wherever that might be? How do you find out how far away something is from its original position? You find the distance between them. That's subtracting, right? We're trying to figure out how far apart they are. The horizontal, then, if you're going to do that, a horizontal shift to the left means you are subtracting a negative number. When you subtract a negative number, that's exactly the same thing as adding the positive. So I'm not sure I've ever even would probably write it that way, but I would just say plus c ultimately. But that's where it's coming from. It's because we're subtracting a negative. You're finding the distance between something and a negative number. That's subtracting a negative. So we're going to talk a little bit about what that's going to look like and how we're going to see those pictures here in just a second. So those are the what we would call rigid transformations, left and right. So those are the horizontals, and then the up and down are the verticals. So let's take a look at the example that they're given in the note-taking guide. So f of x equals absolute value of x. I'm hoping you're familiar with what that equation, that parent graph looks like. We've talked about that V shape. It says write an equation for the function resulting from a vertical shift of 3 and then down, that's important, right? Which direction? And a horizontal shift of 2 units to the right. So we're going down 3, and then we're going right 2. So think about where those values are going to have to go. Love it if you'd pause the video, try to write the equation, and see if you have it correctly, and then we'll check it on our calculator. All right, so let's talk about what those are going to be. Go ahead and pause and do it on your own. All right, down 3 and right 2. So my parent graph is absolute value of x. So here's what I want to do. I want to see if I can make it go down. That's on the outside at the end, subtract 3. That's going to take everything in my function and move it down 3. To go right 2, that means I'm going that horizontal shift that's in with the x. My distance from 0 needs to be 2. So x minus 2 on the inside. We're going to graph this and double check and see if we're accurate. I also want to see if we could write it in function notation though. This is actually the equation I would type into my y equals. What would that look like in function notation? My new function, I'll just call it h of x, would be taking and subtracting 2 from the x, right, because I'm doing that x minus 2, and then subtracting 3 on the outside. This is kind of the function notation version of that. We can write the actual equation, that's the blue one, but in function notation, I'm going 2 to the right, that's going to be inside with the x, and the downward 3 on the outside. Okay, so what I'd like to do is let's graph both of these and see what happens. All right, so I have my two equations in, absolute value of x and absolute value of x minus 2, and then minus 3. So notice the first graph and then the second graph. So I love the color version so you can tell. This new graph has moved the red one 2 to the right and then down 3. So we can definitely tell rigid transformation, right? Same size and shape. Size and shape, easy for me to say, but then it has moved the entire thing in that direction. So being able to understand what these shifts do, huge, big concept that we're going to talk about for every parent graph. The other thing you can use if you're looking for a way to test or to check is to use Desmos, this online graphing calculator. You can do a lot of transformations very quickly and easily on your Desmos as well. There is a link to this in your Schoology. So if you'd rather use Desmos online, feel free to use Desmos and you can type them in there as well, just to double check that the transformations are doing what you think they should. Okay, so let's take a look. Basically, what all of these then, once we put all of these together, you have a family of graphs, each with the same shape, but at a different location in the plane. So they're all basically the same size and shape, these rigid transformations, but they're just at a different location. So they've been shifted somewhere in the plane from where it was originally. So same size and shape, but a different location in the plane. So when we're looking at these, you're going to see a lot of that happening where we're moving them around. So I'm going to go ahead and add an example. I know you don't have extra graph paper at the end, which is kind of a bummer. I just did these along the side because there was plenty of room along the side of example 1, and I just made a sketch. So if you're okay just making yourself an XY axis, we want to talk about the differences between these graphs. So go ahead and get down the information you need. My parent graph is x cubed, so we all know what that looks like. Let's talk about what the transformations are. H of x, adding 5 on the outside. That means every value, every output is going to be raised 5 units up. So this is a vertical shift. So we are doing a vertical shift of up 5 units. So think about the parent graph for x cubed. So my parent graph has the points like 0, 0, 1, 1, 2, 8, negative 1, negative 1. Negative 2, negative 8, this original parent graph. So think of this original parent graph, x cubed, and we are translating or moving this entire graph up 5. Well, you can just do that point by point. Think about that symmetry point. It's going to move up 5, so now it's going to be at 0, 5. The point that was at 1, 1 is now going to be at 1, 6. The point that was at negative 1, negative 1 is now going to be at negative 1, 4. Same size and shape, but it's translated up 5 units. These are the kind of sketches I want you to be able to do. Understand what the numbers do, and then how does that affect your graph. Okay, pause and see if you can do G. What transformation should it be? So go ahead, pause, and then we're going to check and see if that's what you ended up getting. All right, so I think because we have an x minus 3 on the inside, that this graph is going to go right 3, and then because we have a plus 2 on the outside, it's going to go up 2. So this original blue parent graph I have from the last one is going to go right 3 up 2. So what a lot of people do is they take that original 0, 0 point and do that first. So right 3 and up 2. All right, my next point was at 1, 1. That's going to go right 3 and up 2 as well. So go to 1, 1, right 3, up 2. We end up right here. Some people recognize that, wait, it's always over 1, up 1 if it hasn't been stretched. That's another way to think of it. All right, the negative 1 is going to go right 3 up 2 as well, and we get a nice approximation for what that shape looks like. Go ahead and check these either on Desmos or on your graphing calculator to see if you're accurate, and then we'll come back together. So go ahead and pause and see if we can check those and see if they look like you think they should. All right, my first one to check is that x cubed plus 5. So I'm going to go ahead and graph. Sure enough, lifted up 5 units. If you go to your table, kind of cool, you can see all the y values from the original function and look at all the y values from the second function. Everything is just 5 greater, so we can really see that comparison. All right, let's try the other one. All right, we're going to go ahead and put in the second equation and make that comparison. I always like having the parent graph with it on the same screen so we can see what happens. So it went over 3 and up 2. So great way to be able to see that. So I want you to be able to sketch it without having to rely on your graphing calculator. So when we do the kind of check-ins for this, no graphing calculator, I want you to be able to sketch it without. But great thing to check as you're working through moving forward. All right, so let's talk about the next thing. So we talked about the rigid transformations. Now we're going to do the reflections. You can either reflect over the x-axis or you can reflect over the y-axis. So when we talk about reflections, it's what value is changing. So if you flip something over the x-axis, we talked about these symmetries before, the y value changes sign. So that means if you have f of x, then you also have to have opposite of f of x. In other words, the y, the output changes sign. So if you have xy, you have x opposite of y. That would be an x-axis reflection. If you're going to have y-axis, what changes sign? Well, it's the x value, right? So that means if you have the point f of x, you have to have f of opposite of x as well. So if you have xy, you have opposite of x, opposite of y. So, or opposite of x, y, pardon me. So the x changes sign. So it just depends on which way you're flipping. So we want to see where that negative is. If it's out front of the function, we're reflecting over the x. If it's in with the x, we're reflecting over the y. All right, so take a look at this function. We already did this parent graph once today. Look at where the negative sign is located out front. I want you to make your best guess at what you think that is and describe the transformation that's happened. Check it on your calculator. So what did it do? So pause if you need to. Out front, this is going to be a reflection over which axis? Has to be x. Now, you can't ever just say it's a reflection. Yep, it's a reflection. Over what matters? So over the x-axis. So I'm going to go ahead and type that in so you can see it. Okay, so here's the two equations. First one, regular, and then we've got our nice little reflection. I'm curious, if you did the reflection over the y-axis, what would happen in this situation? So if you are looking at the original, we had our graph of absolute value of x. If we did the opposite out front, we had this. I'm curious what you think would happen if we did absolute value of opposite of x. What happens if we put the negative on the inside? What's the symmetry supposed to be, or the reflection? It's supposed to be over the y-axis, right? So what would happen if we reflect this green graph over the y-axis? Isn't it symmetric with respect to the y-axis? Check it on your calculator and see what happens. When you put that in there, okay, so take a look. I just put that in there. Watch that third graph. Oop, went right over the top of it. If it's symmetric with respect to the y-axis, when I graph with that negative in there, it's going to go right over the top of it. Everything that was on one side goes to the other. So if that symmetry is built in, kind of cool. You may not even be able to see that that reflection even happened unless you understand from the equation that that's what it did. So reflecting over the x-axis, reflecting over the y-axis. So that's doing a different kind of transformation in your graph. All right, so let's try a couple with a different parent graph. So this is, again, one I would like you to add. Again, I think you have enough room off to the side to do that. Let's take a quick peek. So we want to compare the graphs with this parent graph. So let's get a handle on what this parent graph is first. This one is a square root that's already been shifted 1 to the right. So let's see what's going to happen. Let's notice what's going on with each of these here. So we have a minus sign out front. Same function on the inside. If the negative's out front, what kind of reflection is that? Well, that should be a reflection over, let's get our guesses here and then we'll check the graphs. Which axis? Out front of the function, that means the y is changing sign, so it would be a reflection over the x-axis. All right, let's take a look at the next one. The negative is located inside with the x, so that means we should have a reflection over the y-axis. And not only that in this one, this is kind of tricky, but I'm going to factor that -1 out front in there. That would be x Minus or plus? Well, negative times a positive would give you a negative. So that would change to a plus 1. So the other interesting thing that happens is not only does this graph reflect, you have to also take a peek at what's happening with that. It's going to also look like the graph is shifting actually to the left 1. We'll talk about why that is, though, when we take a peek. Because if you flip it over, you're going to see why that has to happen. But let's go ahead and graph the first one so we can see those reflections. So go ahead and pause and get your parent graph typed in, the f of x, and let's just do g of x first. All right, so here's my original function. So we'll graph that. All right, and then now we're going to graph g of x. All right, so here comes g of x. Minus out front, we said it's going to be a reflection over the x-axis. Well, sure enough. Hey, if you remember back to earlier in the chapter, remember we did those graphs and we talked about plus or minus, how that wouldn't be a function because you'd have the top, the blue part there, and the bottom, the red. This is exactly why it wouldn't pass the vertical line test. If we only have the top, then it is a function, so that original. Now notice again, I want to say this. On my original graph, we said this minus 1 means the original square root function was going to go right 1. Take a look at where that vertex is on that graph. We're over here at 1. So that's where that's coming from. Okay, now let's go ahead and type in instead the h of x. All right, so I have h of x typed in there. Watch what happens. So there's your reflection right over the y-axis. So when you look at that negative 1, this graph is going the opposite direction. So we have that symmetry with the y-axis. And notice where the vertex point is. 1 to the left. It moved 1 to the left from the origin. And that's why it's happening, because we have that plus 1 in there then when you factor that out. But that's exactly what you need to have, right? That would be the reflection point for the point at 1, 0. So kind of cool to take a look at what's happening with reflection. So reflection is another thing you can do to your graph, and it can happen for any parent graph. Just remember, sometimes, again, it's hard to see if you haven't had a, or if it has that symmetry initially. Okay, let's talk non-rigid transformations now to finish up our last thing. That means those transformations where the shape of the graph is changed. So the rigid ones, remember, we talked about, those they aren't changed. This is a transformation where it stays the same size and shape. So those are the ones we were doing first. The reflections, the shifting left and right, those are all transformations where the shape of the graph is the same. So that shape is preserved. So the shape of the graph is the same. The non-rigid transformations then are the ones where that shape is distorted. So the rigid ones are only the position changes. For the non-rigid ones, actually the position could change, but more importantly, the actual shape of it, like that stretching and shrinking, can happen. And that's what we want to talk about last here. So rigid ones, those are the ones we talked about already. They stay the same shape. Now we're talking about non-rigid. So, actually, I guess they want us to list these first. So the 3 types of rigid transformations are those horizontal ones that we talked about before. That means going left or right. The vertical ones where we're going up or down. The vertical shifts, and then reflection. So those are the 3 that we've talked about already. So those are the 3 that we've taken care of. So left, right, up, down, and then reflections. So let's talk about the ones that aren't rigid. So what does that mean? What does that look like? So there's really 4 types that can happen. We'll talk about all 4 of them here. So you can do something in the vertical direction. So you can vertically stretch, and you can vertically shrink. So there's a vertical stretch and a vertical shrink. We'll talk about what that looks like. And then you can do the same kind of thing, but in the horizontal direction. So you can do a horizontal stretch, and then you can do a horizontal shrink. Now, each of these has a pretty similar effect on the graph, but different things, a little bit different things can happen when we think about it vertically versus horizontally. So we'll talk about that. We'll show a few examples so you can see what we're looking at. All right, so for original function, we're going to use the real number c. So c is just our constant. If you're vertically stretching, what that means is you're multiplying the equation by that value. So I'm going to use g of x for my new function here. G of x would be some number times the function. That's a vertical stretch when that C value is greater than 1. So say you multiply your whole function by 2 or by 7. That's going to vertically stretch the graph. It's going to look, some people use the word steeper, narrower, depending on what the parent graph is, though. It's much better to think vertical stretch, like grabbing the top and the bottom of the graph and pulling your hands apart vertically. If you could see me right now, my arms are going, but I know you can't, so we'll do the best we can. Vertical shrink, represented by the same thing. We multiply that function by a C, a constant out front, but that's only going to shrink if that C value is between 0 and 1, like multiplying by a half or a fourth or something like that. That's actually taking the top and the bottom and pushing it together. A lot of people say that that graph looks wider or flatter, things like that. The other thing that that can do, if you multiply the entire function, excuse me, by a value, it can also affect any constants at the end of this function. So say your original function has some sort of add something or subtract something at the end. It could actually affect those locations as well. So it could have a multiple effect. Horizontal works very similarly, but see if you can tell the difference. I'll use a different function here. You're still multiplying by C, but notice where the C is located. You're multiplying inside with only the X. That means the only effect it's going to have is this horizontal shrink. It's not going to vertically move where those locations are up and down. So it's a little bit more comprehensive. So if there's a constant at the end, it's not going to affect that. So it's only going to shrink those values horizontally when the C is greater than 1. So like if you have a 2x on the inside, it's going to be shrunk horizontally. What does that mean? Think about like taking the ends, your hands on the end of your pillow, right? And like if when it's all stretched out flat and you push your pillow together horizontally, that kind of squishes up top and bottom, or taking like a marshmallow and pushing it together on the sides. That's a horizontal shrink. You're pushing it together in the horizontal direction, but it looks longer then, right? Because it squishes out both ends, top and bottom. So a horizontal shrink functions a lot like a vertical stretch, right? You're making it taller. The difference is the vertical stretch can also move constants at the end, so the points physically can move up or down as well, whereas a horizontal shrink only makes it a taller situation. So it's a horizontal shrink, vertical stretch, function very similarly. Same thing for then a horizontal stretch. Think about what that would look like. We are going to multiply by something only on the inside again. And again, that's only going to happen when the C value is between 0 and 1, like a half or a fourth, 7/8. So a horizontal stretch functions very similarly to a vertical shrink. Again, how it's different is the vertical shrink, where it gets flatter, also can move where those any constant points might be if you have a constant. The horizontal stretch only affects the X value, so it just makes it flatter. So think of a horizontal stretch, like again, grab the pillow and you stretch it out horizontally, or take a piece of like Laffy Taffy and you pull your hands further apart horizontally, it gets more stretched out, right? So a horizontal stretch is very similar to a vertical shrink, like grabbing something on the top and bottom and pushing down is the same as grabbing something on the ends and pulling apart. So again, my hands are moving like crazy, but hopefully that makes sense when you think it through for your values yourself. All right, so we're going to do a few here so we can talk about what these are going to be to wrap up here. So we're going to talk about the comparisons between these graphs, and we're going to use a parabola, but notice the difference between these. So make sure you add these. Our original parabola does not have a constant. It's just f of x equals x squared. The second parabola does have a constant. It already has been translated up 3. All right, so let's talk about what happens and where these numbers are located. So for the first one, we're multiplying just a number out front. That C value is a 4. 4 is greater than 1. So the effect on this graph when we're multiplying out front, go back to our choices here, we're multiplying out front. So, and the number is bigger than 1, so that's a vertical stretch. So we are doing a vertical stretch for this one. And it's by a factor of 4. It's 4 times as tall, those points, so it's timesing by 4. It's a factor of 4. So it's stretched out vertically 4 times as much as what it was before. Take a look at letter B then, h of x. The number out front is a 1/4. Well, what happens to that graph? That is less than 1, greater than 0. That means that this is going to be a vertical shrink. Or sometimes people say compression. It's going to shrink vertically. It's going to be wider. It's going to be flatter. Now, why do we say just between 0 and 1? Why don't we talk about negatives? Remember, if the number out front is negative, that's doing a reflection. That's a completely different transformation. Let's go ahead and graph these and see what they look like. Okay, first one is the x squared and the 4x squared. So notice the vertical stretch. I didn't have any constant on this one, so it didn't really have any effect on my graph at all. So it just was exactly the same as what it was initially in terms of the constant, I should say, like where the vertex is. But it definitely makes the graph steeper. You take the ends and you're stretching it out. It's in the vertical direction. All right, let's take a look at the 1/4. All right, I'm just doing it as a 0.25, but same idea. You can use a 1/4 as well. Look what happens there. Vertex is in the same location, but it's been vertically shrunk. It's like you've taken the ends of the graph and pushed it down. So we have that vertical shrink happening. If I wrote these in function notation, I think that's important to talk about as well. G of x would be written like this. G of x would be taking the original function f of x and timesing it by 4. That would be that vertical stretch. Same thing with the second one. H of x would be taking that original function f of x and timesing it by a 4th. The number is on the outside. So that's how we'd write it in function notation. All right, let's compare that to this next one. This is really important to talk about. Our parent graph is a little bit different. So the parent graph itself is already starting off with its vertex up 3. So when we think about our regular parabola, we're already starting with a vertex like this. All right, they're actually writing this in function notation. Really important to think about it that way. What does this mean in function notation? That means g of x is putting in 2x in place of the x in the rule. What does that do to your equation then? We end up with 4x squared plus 3. Because the number is on the inside with the x, technically what we would call that is a horizontal. Let's make sure we're clear here. A horizontal shrink. Okay, why is it a shrink? Well, because that number, that C value is 2, which is greater than 1. So when we look back at our chart here, if the C value is greater than 1, that's a horizontal shrink. What do I mean by that? That means if I take the ends of my graph horizontally and push them together, shrink them together, my graph should get taller. All right, so here's what I want you to do. Let's go ahead and graph this one right away so we can see what happens. Okay, ready to rumble. I have those two equations in there. Now let's go ahead and graph. So the first one and the second one. Super cool to see here what's happening is that this is a horizontal shrink. It did not affect that number 3. The vertex is still at the same location, but it did definitely have that horizontal shrinking. So look at the red one. It is skinnier. It's like taking the ends of the blue graph and squishing them in, right? Horizontal shrink. So it was moving in and made that graph taller in the middle. So that middle one was a horizontal shrink. Very similar to having that stretch though, right? It's the same idea. So why do we say them differently? If I had taken this original parent graph here, and I had multiplied instead, so this is the difference that I want you to see, and multiplied the 2 on the outside of the function. So what if this number 2, instead of being in with the x, which makes it a horizontal shrink, what if it had been on the outside? Well, watch what would happen then. Take your function and multiply it by 2. All right, well, what would happen? We would get 2x squared plus 6. Now, what effect was that have on the graph? Well, it's definitely going to be a skinnier graph, but look what happens to the constant. It would move as well. So if your parent graph has been shifted already, multiplying out front by a C value, a C of 2, has more than just that elongating. It also moves the vertex. So you got to be careful how they're writing that in function notation. This would be a vertical stretch then. So this would be stretching that graph out vertically because not only does the value get steeper, it also moves that constant. So let's take a look what that graph would be. right? So I'm putting in that last one. So see how the vertex moved up, and it's also steeper, right, than the previous one, but it has a little bit different effect. So it's important to realize what your original graph is doing and where you're multiplying that number. So if you multiply on the inside, those are horizontal things, shrinking or stretching. When you multiply on the outside of a function, it can also stretch and shrink, but it could also move that constant if you have one. All right, so let's take a look at the next one. Notice where that number is located. So I'm going to be putting it on the inside here. So let's go ahead and calculate that h of x. So I'm going to plug in the 1/2 x for x, and I'm going to square that. So notice also when you put in a value on the inside, it amplifies that stretch even more. So instead of being just 1/2, now it's actually a 4. So that c value out front, having the half, actually makes it 1/4 as my actual multiplication factor for what happens to the graph. So what kind of thing would this be? Well, because it was inside with the x, it's definitely going to be horizontal. Because the 1/2, that c value is a half, is between 0 and 1. That means that's going to be a horizontal stretch. It's taking the ends of the graph and making it longer. It's going to look wider in that original graph. So let's go ahead and graph that one and see what it looks like. All right, so here are my original parent graph, and then the 0.25. Look what happened. Elongated, it's flatter, however you want to say that. You're taking the ends of that blue graph and you're stretching them further apart. That's the horizontal stretch, so that's what they mean by that. So notice again, though, the only effect it had on the graph was just simply making it stretch longer horizontally. If I had multiplied the 1/2 out front of the function, it would have not only changed the steepness, it would have also changed where that constant was. So be very aware of where that number is being multiplied. So outside versus inside does make a difference. It still stretches and shrinks, but it could also move some other things. All right, so now we've talked about transformations. Always double check with your graphing calculator or Desmos, but the idea is if you know what the parent graph looks like and you know what the transformation is, you should be able to sketch and know exactly what that new function should look like. So happy translating. These are some questions that we're going to be working on for today. Double check, though, on the calendar to make sure that that's accurate, and we should be all set for our transformations.